power and energy. If you have any doubts in the comment test or any questions pending from your module, do let me know. For friction, etc., for friction and Newton's laws of motion, we'll send you some hints and explanations for the same. Right, so let us begin with the definition of the quantity work done. So since we are aware of all the concepts of calculus and also vectors, we will understand the general definition of work done first and then come to the specific definition. Okay. So if a force F acts on a body while it is in motion, okay, from some initial position, let's say Ri, okay, to a final position, Rf. So let us understand this in the proper context of, you know, general 3D motion, that kind of thing. So with respect to a three-dimensional coordinate frame, okay, if we have a body which started from this position and took some kind of a path and went to this final position. So as you know, in kinematics, we define the position vector as a vector joining our initial position of the particle with our final position. I mean, we define the position vector as the vector joining the origin of our coordinate system with the point at which the particle is located. That is called the position vector. So here this is the initial position vector, okay, and this is the final position vector. So if a force F acts on a body while it is making a displacement like this, or while it is in motion from the initial position to a final position via this kind of path, okay, then the work done by that particular force is defined as integration of F dot ds from initial position to final position, okay, where what is ds over here. So during this displacement, I mean during this motion of the particle, if very small part of the displacement is here to here, this is called a differential displacement, ds, and during that very small displacement on that particle or on that body, the force acting was F, okay, then the quantity F dot ds is nothing but the dot product of force and a small displacement ds. Now that quantity has to be integrated from the initial position to the final position, okay, so therefore we have these limits, okay. So in words, this quantity is called the path integration of force with respect to displacement. So work done, W, it is the path integration of force F with respect to displacement. Okay. So in this, ds is called a differential displacement. Okay. And F is nothing but the instantaneous force during the differential displacement, ds. Okay. So this is the proper and general definition of work done by force. Please make a note of this first. So it might be a little confusing at first, that the definition, but as we look at examples and see how to apply this definition, it will become more clear to you. So yes, cyclic system we will discuss at a different time. Okay, when we come to the concept of conservative versus non-conservative path forces, we will discuss about what is the meaning of work done in a cyclic path. This is the most general definition right now. Okay. Okay, so let us understand this with a quick example. So suppose we have this situation. We have a force which is of this type. Okay, so this is a variable force along the x-axis. Okay, and a body is moved from initial position, this, to final position, this. Okay, so so these are the units. Okay, so A and B are coordinates given in meters. In the above expression, force F is in newtons, x is in meters, so the constant K is in newton meter square. Now we want to find the work done by F during the displacement from A to B. Okay. Assume the body moves directly along the positive x-axis. Okay. B is greater than A. We'll discuss what happens if this assumption is not in place, that is moving along the positive x-axis. We'll discuss about that case also, but let's start with this. Okay, so let's see how we will apply this definition here. But before that, let's get some perspective about the question itself. So this is our xy plane, let's say. This is the point A, this is the point B. Now, as the body is making a displacement from this point to this point, okay, its overall displacement vector is going to look like this. But during that displacement, the force is not constant, the force is variable. So we have to also understand that while making the overall displacement, if we take one very small part of that displacement, ds, so during this small displacement, how much force is acting on the particle? The force acting on the particle when it is at this point and making this very small displacement, the force is like this. It's acting along the positive this thing. Okay. So for a differential displacement, differential means what? Very small. ds equal to dx I cap, we can write, along positive x-axis. Okay. The work done f dot ds. Now you look at this displacement vector, okay, and compare it with this one, the force. So you can see that this becomes how much? It becomes k dx upon x square. So from some x coordinate, if it is making a displacement of dx along the positive x-axis, how much is the work done during that very small displacement? It is f dot ds given by this. So therefore total work done, or you can say net work done, from A to B, that will become integration of this. So that is integration of f dot ds from the initial position A to the final position B. So here we will have to substitute that. F dot ds will be substituted as k dx upon x square. The position A will have to be substituted with x equal to A. The position B will have to be substituted with x equal to B. And then the solving of this integral will further give us the work. Okay. So just note this down up to here and complete the integration. Now all of you know how to integrate 1 by x square. Okay, so this will be minus 1 by x plus c. So when we integrate this from x equal to a to x equal to b, this will be minus 1 by x from a to b. So as you can see, it will become 1 by a minus 1 by b. Okay, so that will be substituted here later. But just make a note of this first. Yeah, why differential we have to take? Because the force is variable, no? The force depends on x. Yeah, Piyush, that's correct. Very good. Yashmit and Durgesh, we are just applying the definition of work done here because it's a variable force. So we cannot take directly F dot S. If we define work done directly as F dot S, so displacement to यहाँ पे मिल जाएगा. It will be B minus A I cap. But what about the force? The force is variable, na? So that is why we have to take F dot ds for a small displacement first, and then integrate that over the entire path. Yes, that's correct, Samar. Yeah. Okay, so all of you understood the question. All we have done is we have actually applied the definition of work done. Now, what was the definition of work done in general? The general definition of work done is given by this integration F dot ds from the initial position to the final position. So here we are replacing F with k by x square I cap. We are replacing the displacement, the differential displacement with dx I cap, and then just solving this integration. So that's what we're doing here. So this becomes minus k by x limits x equal to a to x equal to b. So it becomes upper limit minus k by b minus of lower limit minus k by a. So as you can see, it becomes, I'll write it like this. Okay. Okay. The other thing you can see here that k was in Newton meter square. A and B were in meters. Therefore, the work done here will be in Newton meters or what we call joules. Okay. The SI unit of work is joule, where 1 joule equals 1 Newton meter. We'll discuss more about units, but in this particular example, you can see how the units are coming from the physical constants. That is K, A, and B are all three are constants here. Okay, so hope this calculation is clear to all of you so far. Yes, that's correct, Piyush. The relationship between Joule and Earth you expressed is clear, is correct. Okay, now once we're a little bit familiar with the general definition of work done, before we come to more examples of the application of this definition, now we will see something very important and also something very simple, that if we have a situation where the force we are applying on the body is constant. Actually, before that, one more thing I forgot. Okay. Now, when we write this definition, you should be very clear about one thing. Work done is integration of F dot ds. When we write this definition, one thing important here is ds is the displacement, or in this case, differential displacement of what? So that is very important. Of the point of application of the force. Okay. The point at which we are applying the force, उसका जो displacement हो रहा है, वो ds है. Now, why this is important? That in case of what we call particle dynamics, okay, the displacement of the point of application of the force is same as the displacement of the particle on which the force is acting. So there's no difference between the two. Okay. So if you're talking about particle dynamics, so if this particle has made a displacement from here to here, so during that displacement, whatever force is acted on the particle, the point of application of that force is nothing but the position of the particle. So there's no difference between the two. So whether we say that it is the displacement of point of application, or we say it is the displacement of the particle P itself, okay, force F acting on a particle P. So what is happening? The point of application itself is P. Okay. So ds is like this. Okay. However, so before you note this down, let me explain the counter example of this, why this point is important here. But when we talk about general rigid body dynamics, okay, in general rigid body dynamics, the situation is slightly different. Okay. So if we have an example like this, where we have an object like this, let's say, like a rectangular block. What is happening is that it is moving from this position under the action of some force like this. Okay. So it is displacing like this only. That is one example. Okay, but a more interesting example here is that suppose a rigid body is again that block kind of thing, is lying like this. Okay, but we are applying a force on it in this kind of manner. We are applying the force like this on it, let's say. So as a result of that, what happens is the body now displaces like this. Now next up, the body goes into a position where it's, let's say, it rotates at the same time it translates. So it goes from this position to this kind of position. Okay, because it is in general going to start moving such that the center of mass will have a velocity like this. At the same time, about the center of mass, there will be an angular velocity. And you have started circular motions, you understand angular velocity concept. But यहाँ पे क्या हो रहा है? The center of mass just has a linear velocity. Okay, there is no rotation. So no rotation means it is what we call pure translation. So in case of pure translation, what is happening? The displacement of the point of contact, okay, is identical to the body's center of mass, that one's displacement. Okay. But when rotation is involved, now in this example, you can see that the point of contact is having a different kind of displacement compared to the center of mass. So here, when the body rotates, okay, then the ds being the displacement of the point of contact or point of application of the force, okay, is not the same as the center of mass's displacement. Okay. So it is for this case, which will come later when we study rigid body dynamics or rotational mechanics. So it is for that case, it is very important to understand that we should understand that ds over here, the proper definition of ds is that it is the displacement of point of application of the force. Okay. This is the displacement of the point of application of the force. So in the case of pure translation, we can just write it as the displacement of the center of mass of the body. But in the case where the body is rotating, it may be translating along with rotation, it might be in pure rotation, it doesn't matter. But in that case, the displacement of the point of contact, point of application of the force will not be the same as the displacement of the center of mass of the body. So that is why it is very important to, from the beginning, in our definition, understand that in f dot ds integration, in that definition of work done, what is ds? It is the displacement of the point of application of the force during a small time dt. Okay. This is the displacement of the point of application of the force, not the displacement of the center of mass of the body. If we are talking about particle dynamics, we can say that it is the displacement of the particle because it's one and the same. If we are talking about rigid body dynamics, then in general we cannot say that it is the same thing. It depends on whether the body is in what we call pure translation or the body is also in a state of rotation. So hence, when you are studying the general definition of work done, it's important that from the beginning you understand that ds has a very specific meaning over here. It is the displacement of point of application of the force. And with the example below, you can understand the difference between the two. It is not the displacement of the body, because in common language, the displacement of the body would mean that it's the displacement of the center of mass of the body. So, imagine you have something like this. You have a rod which is hanging from the ceiling with a hinge over here. And what I'm doing is I'm applying some force at the bottommost point of the rod. So after some time, the rod, after a very small time, comes to this kind of position. Now you can see that the center of mass of the rod has displaced from here to here. So this is the displacement of the center of mass. But the point where I'm applying the force, that is displaced from here to here. So they are not one and the same thing. You can see over here that the displacement of the point of application is not the same as the displacement of the center of mass. Because why? Because the rigid body has rotated. So whenever there is rotation involved, which will come in the later chapter of rotational mechanics, but you should understand it from the beginning. Wherever there is rotation involved, the point of application will not have the same displacement as the center of mass. So please make a note of this point first. However, currently in this chapter, mostly we will be dealing with particle dynamics, okay, instead of rigid body dynamics. So in particle dynamics, we need not make any distinction between the two. When we say displacement, whether we say displacement of the point of application of force or displacement of the particle on which the force is acting, is one and the same thing. So it's not a big deal, okay. But in general, in rigid body dynamics, it is a very big deal. Whether so we should make the distinction between what we mean by ds as displacement of the point of application of the force is not the same as the displacement of the body, because displacement of the body in general would mean displacement of the center of mass of the body. No, Shikhar, what is happening in this case? No, the body is going to move along the negative y direction also. So if I apply a force like this on the body, but because the force is also creating something called torque with respect to center of mass, so it causes a combination of rotation and translation. So the center of mass starts moving like this, but along with that there is also an angular velocity. So after some time you will see that the center of mass is moved from there to here, but the body is also rotated, so it might be in this kind of position. Then later it might be in, by the time the center of mass has come here, it might be in this kind of position. So it's constantly rotating at the same time translating. Just imagine you have kept a rod on a smooth table and you apply a sharp impulse on one side like this at some kind of angle. That rod will go like this, it will go spinning, right? It will go like this, that kind of. Whereas if you just apply a force from one side along the length, it will go straight, it will go translating. Okay. But if you apply the force like this, like this. So it will go into this kind of motion. So combination of rotation and translation, that kind of thing. Or if the rod is hinged at the top and we apply a force at the bottom like this, so it goes into a displacement like this. No? That is what I've shown in the example on the side, on the right hand side. You can see that the force is acting at the lowest point. So the lowest point has a different displacement compared to the center point. Yeah, very small difference, but you're going to integrate them over path. No? So it will make a difference end of the day. No? Like for example, if this is pure rotation, like yes, Smith, like we've taken in the example on the right, the rod which is hinged at the center. So this is basically what it is, like an arc. No? So this arc has radius of L by 2 for the center of mass, whereas the point of application has a radius of L. So it's a 50% difference now. So percentage difference wise, it's huge. So we have to make that distinction very carefully. Okay. So especially you will see that when we apply the concept of work done in the chapter called rotational mechanics, which will come a few chapters later, this is something you have to take into consideration. Okay. As I said, currently we will not be too bothered with it because we are dealing with particle dynamics. But the moment we come to proper rigid body dynamics, after doing the chapter center of mass, this will come into prominence. Okay, so having understood this, now next quick thing is about the units which we have indirectly already discussed. So SI unit is joule. So 1 joule is equal to 1 Newton meter. Okay. CGS unit on the other hand, it has a specific name. It is called erg. So 1 erg is equal to 1 dyne centimeter. So dyne, as you know, is 10 raised by minus 5 Newton, and centimeter is 10 raised by minus 2 meter. So that makes it 10 raised by minus 7 joules. So that is the relationship between the CGS unit erg and the SI unit joule. Also dimension. So incidentally, at a later stage, we will see that work and energy have the same unit and dimension. And that is not a coincidence because the two are very related to each other. Yeah, Srishti, I'll explain the whole particle versus rigid body dynamics. See, when we are applying a force on a particle, the particle will have the same displacement as the point of application of the force, because particle is a point mass ना. So particle पे मैं जहाँ पर भी force लगा रहा हूँ वही तो particle का position है. So there is, if I am applying the force on a particle, the particle is the same as the point of application. So if the particle displaces from here to here, the point of application of the force is also making the same displacement from here to here. There's no difference between the two. But when I'm talking about a rigid body, that is when the difference appears between the two. Now imagine there's a spherical body like this, lying on a rough surface. Now this is the center of mass of the spherical body. Okay. But suppose I'm applying the force at this point, right at the top. Okay. And suppose as a result of this, what happens is that this goes into this kind of motion where it is both spinning and translating. So then where will that point of application have moved? The point of application would have moved somewhere here, whereas center of mass is moved from here to here. So the two displacements are not the same. Na? The point of application's displacement, as you can see in the diagram clearly, it is different from the center of mass's displacement. So in that situation, we have to make a distinction that in the definition of work done, what is the displacement? It is the displacement of the point of application of the force and not the center of mass of the body. Whereas in the case of a particle, we don't have to make any distinction because the particle's displacement is the same as the point of application's displacement. Is it clear, Srishti? Okay, very good. Okay. So this is a conceptual part, okay, and which is why I would also urge you that after today's lecture, you also read the relevant parts from resting holiday. It will give you good explanations, the type of explanations we are discussing in class now. It will give you complete proper explanations. Whereas HC Verma will give you very short descriptions, which are okay for problem solving, but for your own proper conceptual understanding, it will help if you study from a good reference book like Resnick Halliday. Okay. Anyway, now coming to something very important. Work done by a constant force. Okay. So what do we mean by constant force? The force F has a constant magnitude and direction. Both the things should be constant. Neither direction should be changing. Okay. During the entire motion. From initial to final position. So when this happens, the work done which is defined in general as F dot ds from initial to final, because the force is constant, it becomes F dot integration of ds. So it becomes F dot s. So the definition of work done becomes much simpler when the force is constant. In fact, this is the definition that you would have learned at the 9th-10th level, that it is force multiplied by displacement in the direction of force, which we'll understand by the vector definition of dot product also, that it is force into projection of the displacement along the force. So we'll come back to that, but note down this first. Okay. So when the force is constant, the definition is much simpler. For constant force, F, work is equal to scalar product of force and displacement, where remember displacement is the displacement of point of application of the force. So make a note of this first. This is very important. Okay, so let us yeah, I will come back to the part above. Many of you have not written that, but first note down this section, then we'll come back to the part above. Okay, finish writing this down first. Okay, so let's understand this concept once more. So suppose we have a situation where a particle is making a very complicated kind of displacement like this, going from here to here. This is the initial position, this is the final position. But during that displacement, the force acting on it is always constant. The particular force that we are talking about, which is acting on it, that is constant throughout. And that vector looks like this. When it's here, that force is like this. When it's here, like the force is like this. So throughout, it's making the force vector is an arrow which neither changes magnitude nor changes direction. So what will happen is when we take a small displacement like the ds over here, to make the calculation simple for us, what we can do is, because the direction and magnitude of force are both fixed, we can take the direction of the force as our x-axis. We can define this itself as our x-axis. Define this as our y-axis. So the force F being a constant force, okay, suppose we choose F's direction as I cap. Okay. So then we can write the force as F I cap, where capital F, which is the magnitude of the force, is constant, because we know that this force is a constant force. Okay. Whereas the displacement ds, it's general, as you can see. So it'll have all three components: dx I cap plus dy j cap plus dz k cap. Okay. So now when we apply the definition of work done, that it is integration of f dot ds. Now you see, when we take dot product of these two, we will get what? We will get integration of f dx from initial position to final position. So that is f into x of final minus x of initial. Now you see, this thing is nothing but dot product of force and displacement, because the displacement from initial to final position, the net displacement, that is going to be this vector here. From initial to final position, the displacement is this vector s. So if s is this, it is x final minus x initial I cap plus y final minus y initial j cap plus z final minus z initial k cap, because the initial position has coordinates xi, yi, zi, and the final position has coordinates x final, y final, z final. So this is how we'll write the displacement. Okay, this is the initial position, this is the final position. So this is how we'll write the displacement vector from initial to final. Okay. So now when you look at this quantity here and you connect it with this definition of the displacement, so you can see that this is nothing but the dot product of force and displacement. So this is another way of expressing that why, in other words, we can see that because force is constant, we could have skipped this integration step and we could have just written that it is f dot integration of ds means f dot s. It's one and the same thing, but provided the force is constant. Okay, so hope this is clear. Just make a note of this also. नहीं नहीं, वो क्यों हो रहा है ऐसा देखो ना बेटा, बिकॉज when you take this dot product na, f dot ds, it's f I cap dot product with this na. So what this dot product will give you here, see this dot product f dot ds, it is f I cap dot product with dx I cap plus dy j cap plus dz k cap. Now remember dot product of two vectors now, it is x components का product, so f dx plus y components का 0, z components का 0, it is f dx. Okay, where f is now a constant, so integration f dx will become f into integration dx from initial to final. Is it clear now, Shikhar? Yes, that is why, because the force is only along the x-axis, you know. We have chosen our x-axis to be along the direction of the force for that convenience. So ultimately, when you compare the expression that we are getting with integration with the dot product, you can see it's the same. So we are directly taken the dot product as per the definition above is one and the same thing. Okay. So this becomes very important. Okay. And along with this, what also becomes very important is the fact that for a constant force, okay, work done being defined as F dot S, work done for the constant force is independent of the path. Okay. And only depends on displacement S. Okay, so let me explain this. So if we are going from point A to point B, okay, my displacement vector is this one. Okay, this is my displacement vector. But if I choose two different paths, I have one path which is going like this, say like this. This is path one, let's say, and I have another path which is considerably simpler. Let's say it's going directly like this. But work done by some constant force from A to B will be identical for both paths. So it does not depend on the path. So even though it is coming from the definition of path integration, it is independent of path. It only depends on the displacement. In the case of constant force, in the case of variable force, we still have to discuss more about this. Okay, whether the force is the work done is path independent or not. So this is showing you that the work done is independent of the path. So hope this point is also clear to all of you. Okay, now let's do a simple example. Okay, so we have this rough inclined plane. So a block of mass m equal to 10 kg slides down a rough inclined plane. Okay, mu equal to 0.5, let us say, from A to B. Okay, 20-meter displacement. Calculate the work done by each of the forces separately in joules. Each of the forces acting on the body. Calculate the work done by them. Just try out this question, people. So first of all, you understand how many forces are acting on the body. Okay, and what are these forces? Then you calculate work done by each. And for work done here, you can just apply the definition F dot S, because all your forces will be constant. There's no variable force acting over here. Okay, so these are the work done by which all forces? Parth, your answer is correct. Piyush, your answer seems to be correct. Devansh, could you tell me work done by which forces? Okay, work done is a scalar quantity, Piyush, so remember that. Acha, you've written joules. Okay, that's fine. Okay, so this is pretty simple actually. So you can see what all forces are acting on the body. Let's start with that. And we don't need not worry about, displacement or point of application or whatever, because here the body is not going to rotate. So there is mg acting, there is normal reaction acting like this, and there is friction acting like this. So these are the three forces acting on the body. There is normal reaction, there is kinetic friction, and there is mg. And from Newton's laws, that this angle will be 37 degrees and all that. So normal reaction will be mg cos theta. So more importantly, kinetic friction will be mu mg cos theta, which in this case will become how much? It will become zero point 0.5 into 100 into cos 37. So that will become 40 newtons. Okay. Whereas, okay, mg itself is 100 newtons. This is 80 newtons. Okay. Now the displacement vector that you can see here is very simple. It is along the inclined plane, and its magnitude is how much? 20 meters. So this is the displacement. So most importantly, this angle is 90, this angle is 90, and this angle is how much? It is 53 degrees. So there you are. You have to just apply this in the definition now. So work done by gravity will be mgs cos 53. Okay. So it is 100 into 20 into 4 by 5. Okay. Sorry, into 3 by 5 minus 2. Cos 53 is zero point 0.6 or 3 by 5. So positive of 1200 joules. Correct. Work done by normal reaction will become n into s into cos 90 degrees. That's 0. And work done by friction will be kinetic friction into s into cos 180. So that will become minus of mu mg cos theta into s. So that will become minus of 40 into 20. So minus 800 joules. So these are the work done respectively by each of the forces. Three forces, out of that one is doing zero work, the other two are doing, one is positive, the other is negative. So now this becomes the work done by gravitational force plus work done by normal reaction force plus work done by friction. The order in which we write doesn't matter. So it's 400 joules. The net work done is positive of 400 joules. So free body diagram becomes something important in work by energy chapter also, okay? Because when you're calculating work done by the forces, it's very important to understand the direction of the different forces acting on a body with respect to the direction of its motion or displacement. Okay, so hope this example is clear in all the respects. Anna, you have understood work done by normal reaction? Okay, so we are just using the definition F dot S, because all the forces are constant. All three forces are constant, so we are just going by this. Okay. Now, when it comes to F dot S, we'll see there's a way of interpreting it also, so that we can make the solution a bit faster. So, this formula for constant force. Okay. Let us look at the interpretation of this. So, suppose force like this is acting on a particle which is making a displacement like this. So, a particle is displacing from this initial position to this final position. Okay. This angle is theta. So work done, which is F dot S, by definition it is Fs cos theta. Now we can think of this in two ways. We can think of it as F cos theta into S. So if we think of it like that, what we are doing is we are taking the component of force along the displacement. This is our F cos theta. So this is the component of force along the displacement. Remember that projection concept. Okay. So it is component of force along displacement multiplied by magnitude of the displacement. This is one interpretation. Okay. Now the other interpretation of the same thing is that we could also think of it like, what is S cos theta over here? Okay. So the force acting is this, and it's acting along this line, whereas the displacement as you can see in the diagram, is like this now. Suppose the displacement is like this. This angle is theta. So we can also think of this as f multiplied by s cos theta. So in this diagram, you can see what is s cos theta. You have to drop this perpendicular somewhere here. So this is my s cos theta. Okay, it is the projection of displacement on force. So you could also think of it as force multiplied by the component of displacement along force. So there are two ways of interpreting it. Okay, either you can divide the force into components, parallel component of force multiplied by displacement, or you could divide the displacement into components and work done becomes force into the parallel component of displacement. It's one and the same thing. It's basically part of the definition of work done. I mean, definition of scalar product. When we write the scalar product of two vectors, A dot B, which is AB cos theta, you can think of it as the parallel component of A into B or A into the parallel component of B. It's one and the same thing. So that's where the projection concept also becomes important. So when we're doing dot products, I told you that the first time you will see the importance of dot product and the concept of projection will come in work by energy. And this is what it is. शिखर, I didn't understand theta 1 and theta 2 क्या है आपके लिए, मतलब ये दोनों एक ही एग्जांपल है यहाँ पे, है ना, they are one and the same example, but I'm just interpreting it in two different ways. This diagram is the same as this diagram below. Okay. Okay, so hope this interpretation is clear. Now next we'll see a very interesting situation. We'll see a situation where we have a particle sliding down a slope like this. is going to be a frictionless surface, but such that the angle of inclination is not fixed. So it's a curved slope. Instead of being a normal sort of straight inclined plane, it's a curved slope. The kind of thing which is more common in real life. So this is a smooth curved slope like this. Okay. And this height is, let us say, 10 meters, and this width over here is 20 meters. Okay. Now a particle is released at this point, and eventually it comes to this point. It slides down to this point, and by then it has some speed v. Okay. So a particle of mass, suppose 2 kilogram, slides from A to B down the curved smooth slope. Okay. Take g equal to 10 meters per second square. Calculate work done by gravity or by the weight of the body, and work done by normal reaction. Okay. So this is a very interesting problem. Just try it out. Remember the basic definition that we have talked about. Okay. That work done is F dot S, or constant force, whereas work done is integration of F dot ds in general. Okay. Especially for variable force. So to be careful about which definition you're applying for which part. Okay, so I've given you a hint. Just try this out. Yes, Devansh, your answer is correct. So far, Viraj, your answer for work done by gravity is correct. Samarth, your answer is correct. Piyush, your answer is correct. Devansh, your answer for both parts is correct. Okay. Rest everybody seems to be getting slightly different answers. So anyway, let me first give you the answers, then I'll explain how. So work done by gravity should come out to be mgh over here. In words, when you calculate, it will be like that. So it will be if you take g as 10, so 20 newtons into 2, so plus 200 joules. I mean 20 newtons into 10. Whereas work done by normal reaction, interestingly, will come out to be 0. Now let's understand why that happens. See, the way we calculate each one will be different. Okay. So what we have to be mindful here is that mg or weight, it will be a constant force here. Okay. The weight as a force, or you can write it as mg as a vector, will be minus mg j cap always. If you take this as your x and y axis, so it doesn't matter what the path is. The gravitational force acting is always constant, as it's going like this in this path. So whatever be the path. So work done by gravity will be dot product of this with displacement. Okay. So you can see that if the displacement vector is this one, you can see here that if the displacement vector is this, then the projection of the displacement vector along mg, that is going to be how much? That is going to be this one, h. This angle is theta. It's going to be mgh. This height is h. This is h. Okay, so this is how we do the first part, the calculation of work done by gravity. Yeah, and I hope this is clear. As the object is sliding down the, you know, along the curved path, gravitational force so constant, है ना बेटा, it's always acting vertically downwards and of magnitude mg. So what definition of work done we will use? The dot product definition, F dot S. So we have to find the force into the component of displacement along force. So component of displacement along force क्या है? देखो force ऐसा है और displacement ऐसा है. So S cos theta कौन सा component है displacement का? Vertically downward component है. ये है ना? This is our S cos theta. That is nothing but H. Okay. So Anay, you have understood this now. Why we got it as mgh finally? It's from that interpretation. It is force into projection of displacement along the force. So projection of displacement along gravity क्या है? उसका vertically downward displacement है ना? वो h है. Okay. So matlab, you don't even need to do all this calculation. Once you are clear with the interpretation, you can see that gravity is acting vertically downwards. Okay. So what is the projection of the displacement from A to B? Here you can understand that projection of the displacement A to B along gravity, that is basically what? That is h, because gravity is acting vertically downwards. So therefore work done by gravity will be mg multiplied by that projection. Now let's come to the normal reaction part. Now normal reaction here, interestingly, this is a variable force. Why it is a variable force? Because it acts always normal to this plane of contact. So if you compare the body when it is here, for example, or the particle when it is somewhere here, this is the direction which is tangential to the surface at this point, let's say. So normal reaction will act like this on it. Okay. Whereas compare that to when the particle is somewhere here. Now when the particle is here, the direction which is along the surface or tangential to the surface is like this. So normal reaction is acting like this. It's acting along this line. Okay. So at any given instant, if the tangent to the surface at that point is at an angle theta with this, normal reaction is changing both in magnitude and direction. Changes in both magnitude, because at any point n is equal to mg cos theta, but theta is variable, and also changes in direction, because theta, the slope of the tangent, I mean tan theta, is variable. Okay, so normal reaction is a variable force. So work done by normal reaction हमको कैसे निकालना पड़ेगा? By integration of n dot ds. Now how we'll do this integration? Luckily we don't have to do this integration, because we can see that whatever the normal reaction is at any given point, the displacement ds is always perpendicular to it. So the differential displacement at this point will be like this. The differential displacement at this point will be like this. So this luckily will always be nds cos 90 degrees. So this will always be 0. Okay. So the important thing here is this, that at any point during the motion, the differential displacement, this is along the tangent to the curved path. Okay. Whereas normal reaction is along the normal, that is perpendicular to the surface. Okay. Therefore perpendicular to the tangent. Okay. So therefore n is always perpendicular to ds at all points. Okay. So that is what is coming in here. So this becomes a very important aspect of the application of the work energy, I mean the work done concept over here. So though normal reaction is acting in a very complicated way here, as the body is moving continuously, उसका magnitude and direction दोनों change हो रहा है. But we don't have to worry about that complication because in our dot product, the angle between n and ds is always 90 degrees. So the work done by normal reaction is coming zero. Okay. I mean, this is not a general rule. It doesn't mean that always work done by normal reaction will be zero. But yes, in a case where a body is sliding down a surface, okay, like this, it could be a rough surface, it could be a smooth surface, it doesn't matter. It could be a a regular inclined plane with fixed angle theta, or it could be a curved inclined surface like we've discussed here. The work done in such cases by normal reaction will be zero. Okay, so this is something very important over here. So finally, work done by normal reaction is zero. Whereas gravity is doing positive work of 200 joules, or more importantly, mgh. Yes, I'll show the first part also. Okay, so people, with this we complete today's session. Now we've covered a lot of ground in this, so I will be sending you uh, along with the notes a worksheet also, and the worksheet will also contain some reading work for you to do. Preferably, you read about those topics from Resnick Halliday. But if Resnick Halliday is not working out for you or is not available to you for whatever reason, you can also read from the module or from H.C. Verma. For that matter, you can also use NCRT as a reference. But the preference for me will be if you use Resnick Halliday for your theory reading reference work. Okay. And of course, we will be doing H.C. Verma's exercises also in this chapter. So next lecture is going to be very important. We are going to discuss about the relationship between work done and kinetic energy. Okay. And we are going to discuss about work done by spring force. If you remember, we discussed about spring. In fact, we will do a bit more discussion about springs in general after we calculate the work done by spring force. Okay. And we will also see something called conservative and non-conservative forces. So these are some of the aspects that we'll be looking at in the next lecture. So I'll give you some reading work so you can read up a bit ahead and come also next time. Now, a lot of numerical problems can be solved by just using these concepts that we have discussed today. Okay, work done by constant force directly F dot S, work done by variable force integration F dot ds. So there will be some numerical problems which you will be solving using these concepts itself. Yeah, you can solve some of the questions. I will send you in the this thing. Okay, not all the questions of H.C. Verma yet because we have to learn about the relationship between work and energy, work and kinetic energy, etc. That is called the work kinetic energy theorem. Then we also have to discuss about potential energy. Okay, by the time we discuss about these two things, potential energy and the relationship between work, kinetic energy, and potential energy, then you can solve all the questions in H.C. Verma. But yeah, the beginning few questions I will send you a list you can solve by just using the definition of work done and the formulae that we have discussed today. Okay. So that's it for today's session, people. All the best.